Welcome to our panel discussion, hosted by Tony Orme from the Broadcast Bridge and other distinguished history. I'm going to let Tony introduce his panelists. And this is designed to be an interactive session, so Tony's got some questions prepared to talk with these folks with, but also this is a chance for you to really get some personal insight from some true industry experts. So we'll be here with the microphone ready to help get you with any help you ask your questions. So thank you. Take it away, Tony.
Great, thank you for coming along this afternoon. I'm the editor of the Broadcast Bridge, and the Broadcast Bridge excels itself on creating technical content, really good technical content, to help you make informed decisions about the technology you might want to use in the future. So today's panel is all about trying to make ST2110 systems work and what we need to do that. So with the panel with us today, and I should say, if you have any questions as we go along, please just raise your hand, and we will, we'll invite questions as we're going along. So at the far end we have Paul Harding from NAP. Next to him is Gerard Phillips from Arista, Phil Myers from Lawo, and Daniel Boldt from Meinberg. So my first question for the panel is, where do you start when you design an ST2110 system? What are the first considerations? So, Paul.
That's an interesting question. I mean, fundamentally, you need to start by thinking about the scale of what you're trying to build. So, and then a lot of the answers fall out from that. So, how many inputs, how many outputs, what equipment am I connecting, what data rates is that equipment, is it 10 gig, is it 25, is it 40? And then from that you can start to make an informed choice on switch size, but also enables you to make decisions on timing and control systems and so on and so forth.
Okay, Gerard.
Yeah, I'd echo that. I'd say that understanding your start size is very important. I'd say that you really need to understand what your size needs to be in 5 years' time. What is your aspiration? How are you going to grow? You need to have a think about whether that brings the need for some sort of orchestration, PTP architecture. Yeah, that's probably it.
Okay, Phil?
I think from my side, it's looking at the individual workflows and whether they can be met today with 2110 and how you work that in. So things like audio workflows, where you may have devices that can only receive a single audio stream with every video. How are you going to get around that? How are you going to do things like audio breakaway, audio shuffling, alignment issues that might come around as you go through multiple devices. Things like contribution links, where you may need some form of compression, how you're going to build that into the system as well.
Daniel.
Yes, and I'm more from the timing side. I need to emphasize on the fact that you need to take care about PTP and timing, not only at the later points from the beginning. So that is because this is the essence, the core of everything.
Okay. Something that really plays into how you choose your architecture is whether you need geographic dislocation.
Okay.
Do you have multiple sites? Do you want to build a system that has connectivity in multiple rooms or multiple floors? Can you build a centralized system, or do you want to build a distributed system?
And I think we'll come on to that in more detail a bit later. I mean, I'm interested in what you're saying about inputs and outputs, because in traditional SDI systems, the inputs and outputs are quite obvious because you have a one-to-one mapping. But it gets a little bit interesting in IP, doesn't it? Because you can have many inputs on one physical connector. So how do you account for that? Gerard?
Well, I mean, then you're down to failure domain size, you're down to your broadcast vendor solution set. What do their gateways look like, or what do their multi-views look like? What density have they implemented? So 10 gig has been around for a long time. 40 gig is an aggregation of 10 gigs. That's very smart. 25 works quite well for UHD, and 100 is really good for multi-viewers and vision mixers and large users of data. So in my terms, having been at Snell for a long time and worked on the stuff at the kind of gateways they built, you can think of you got to think in terms of multiple flows per link, and you've got to think about full duplex. Those are two things we never had with DNC. So you'll get the best efficiency if you're thinking about endpoints that both need and deliver sources, because you're using the 100 gig link is a 200 gig link, really. There's 100 gig out, there's 100 gig in. You may as well try and use that. So most efficiency will come from thinking out of the box in terms of not it being BNC connections anymore, but in terms of it being bandwidth that you can use both ways.
Okay. And what does one of these connectors actually look like? I mean, you know, I'm thinking IPs, an Ethernet connector. It's a little RJ45. Is that the case? Or
So if you told me you were going to ask that, I'd have brought some. So they come in, so audio is typically RJ45, a gigabit, for example. Video streams will be on 10 gigs or 25 gigs. That's an SFP. That's maybe that big. You get 48 of those in a 1RU. 100 gig or 40 gig comes in QSFP, which is maybe 1.5, maybe 2 times that size. We're shipping 400 gig switches now. They come in a thing called either QSFP DD, which is the same physical size as the 100 gig, but 4 times the capacity, or OSFP, which is very slightly bigger, but has other benefits.
Okay.
So yeah, big density.
And Paul, when you were putting your systems together, the actual choice of connector, I mean, how did you break that out? Because you say you've got all these multiple like cameras or video feeds going into one port switch. How do you physically do that?
Well, I mean, so there's a variety of ways of achieving it. It depends what you're trying to do within the solution. So for some equipment, it's as simple as a direct connection. So you have a single cable. There's multiple options. You don't have to use active optical solutions. You can use copper cables if you're within, you know, 1 meter or 2 meters or so from the kit. But as we start moving away, it also depends on the flexibility that you're looking for. So for the QSFPs that Gerard was mentioning, there's multi-way cables called MTP or MPO. So that enables you to connect all 4 lanes across. A lot of the stuff that we did within the Wimbledon system was then broken out into individual lanes of either 25 gig or 10 gig through patch base, so that you could then connect different pieces of equipment into the same solutions. The other key thing to bear in mind as well is the distance that your kit is. So if you're within a 50-60 meter radius of the equipment, then everything can run on multi-mode fiber. And that means that the optics are slightly more cost effective, shall we say. But as soon as we move outside of that range, we're moving to single mode optics and single mode fiber. And so you have to bear that in mind and look, as Gerard said, sort of geographically in terms of the system, how far am I trying to get away from my central switch, or how far am I trying to put my satellite switch from my central switch, and you can start to determine what those connections are and what that level of connectivity is that you require.
Because one thing I've always thought about, with an IP truck, for instance, the old days of broadcast vehicles, you'd have a big umbilical going to the back of the truck, or hundreds of connectors coming out of the truck. But when you connect a truck, 2 trucks together now with IP, what does the IP connector look like?
Well, it's an interesting question.
Is it just a little something
yeah,
like,
I mean,
my pen like this?
so it very much depends on the choice of connectivity. So if you were connecting with long-range optics, for example, then they tend to have built-in CWDM. So you just end up with an LC pair. So 2 small fibers on LC. In terms of ruggedness on the truck, you wouldn't want to expose such a small connector to people kicking it and breaking it, etc., etc. But then there's a whole host of different connectors that you can utilize. I think initially for the trucks that were built in the UK, the idea was connect over MTPs, but you know, more ruggedized solutions are now sort of being deployed.
If you think about a GV camera,
Yep.
attached to its CCU,
Yep.
that's an LC pair inside a ruggedized cable.
Right.
That is already IP, unicast IP. So imagine, and that fiber would support, well, currently it's 10 gigs, but it would support 25 or 40 or 100 or 400. So yeah, ruggedized connectors are completely available.
Okay, all right. Daniel, as far as timing is concerned, when we have a time, we have a master clock, a master PTP clock.
Yeah.
Where in a network does that have to be inserted? Can it be anywhere, or does it have to go into a specific place? Can you just connect it to the master switch? How does that work?
Basically speaking, it could be anywhere, because if every switch in the network is, for example, a boundary clock, then PTP is transferred to every location in the same level of accuracy, at least the level of accuracy that is needed for SMPTE 2059. Usually would put this grandmaster at a spine switch,
Yep.
but the problem is that there's mostly a minimum link speed on the spine switch, and therefore a grandmaster, which is usually has a 1 gigabit port, is put on a leaf switch.
Okay.
But as soon as also this technology is evolving and also 10 and 40 gigabit grandmasters are on its way,
Yep.
they can also be placed on spine switches. But I also saw once a construction of a chain of adapters that could also put a 1 gigabit grandmaster onto a spine switch that is
Right.
usually also having 100 gig ports. So it worked.
Okay.
With the very special adapters, but the usual way is that you put it on a leaf switch.
Okay. And that would allow you to aggregate lots of other sources into one connector to go into the spine. Is that correct? So you have the leaf switch, and then you have that would then allow that to connect to the spine switch.
Yes, of
Right.
course. Yeah.
Okay. Phil, I was over at the Lawo stand a couple of days ago and saw this big new monitoring system you have, and I was intrigued to see how the data was presented. So you were connecting to an Arista switch, I believe.
Yep.
Using
OpenConfig.
OpenConfig, thank you. And then you were extracting data out of the switch,
Yeah.
which you were then presenting. How did that work?
So that's a smart product. So what we do is we connect to the fabric,
Yep.
and we basically get all the streaming telemetry from the Arista switches. And what we do is we get all of the flows that are in the fabric, where they enter, where they exit, where they live.
Yep.
And then we correlate that through the control layer to give it some logical name. So rather than an operator have to remember what multicast address is associated with which camera, we present it in the same system. So you can do a couple of things. We can look at the fabric and see if it's all timed correctly.
Yep.
We can look at the fabric and see if there's any blocking on any of the ports. So we actively monitor ingress and egress for every link in and out. And we're also looking to see if there's any fault state on any of the switches through the fabric. Additionally, we're also looking at the actual flows themselves. See if there's any timing issues. We can look at audio and video to check for AV alignment issues. We can also look to see if there's any packet loss. So for example, if I'm looking at a video, it may well be that it's impaired, it's got lines on it, and the logical nature is it's the fabric.
Right.
But actually what it might well be is one of the video that's entered, or it may be the video device that's left throughout. So we provide this true telemetry throughout the entire system. But the nice thing is we store all of that data, so you can completely rewind it back.
Yep.
So if at 5 o'clock yesterday you had an outage, you could run it back and see all of the state of everything at that point in time.
Okay. And so Daniel, when we get these timing issues that Phil referred to, how do they manifest themselves? What causes the timing problems?
Timing problems are caused by many different factors. Mostly issues in the network. If you don't have a fully PTP compliant network, then the load and the traffic on those switches are impacting the variance in packet delays, and this directly affects the accuracy that you can achieve at the end node. But if you have a fully PTP compliant network, then you should not have these kind of problems that depend on the traffic on those switches. But you need to keep in mind that boundary clocks, so boundary clock switches, are real clocks. So they have a real clock inside, and also they can have problems besides the master and the slave, of course.
Right.
So monitoring of all the components, including the boundary clocks, is definitely recommended.
And when you say monitoring, what exactly do you mean by monitoring? How do we monitor PTP clocks?
You can monitor two different things. You can monitor the PTP traffic itself,
Yeah.
which tells you the master-slave relationships, which slave is connected to which master, over which boundary clock, and so on. And then you ask your end nodes and your master itself about the status. So tell me what your status is. Are you locked to the master? Are you fully synchronized or not? Then this end node will tell you what it thinks it is. And then the best way, but not yet possible all the time, is to actively measure the end nodes and the masters from an independent monitoring system.
Okay. And is there a way to measure the frequency of the clock and the accuracy?
Yes.
Yes. And how would you do that? Is that a piece of software, or is it a oscilloscope, or how do you do that?
There's a kind of extension to PTP that my company proposed.
Yep.
We hope to get it into the official PTP standard at some point in the future.
Yep.
That can do some kind of reverse PTP, so that you can actively measure a slave and measure its accuracy back to a monitoring node.
Okay.
But I think just to add to that, there can be scenarios where timing issues can be occurred as audio and video transits through devices, and devices that don't do AV alignment based on the RTP timestamps. There can also be misalignment issues where you've got flows coming from multi-hops away, and again, just getting them to align at a given sort of timing plane in the system. And I think the whole point of having a monitoring system is to see where you need to make the adjustments if needed.
Right, so when you say multi-hops, you mean sort of further switches down
Could be
the line?
further switches away, could be switches that have been carved for multiple VLANs, it could be, again, they just transit through different routes to get to the final destination.
Okay.
Yes.
And Paul, could I ask you, from a practical experience of making all this work, what kind of timing issues? Is there a common timing issue you see, or is every case different?
I don't think in a lot of the systems that we've put in, we've seen many timing issues. One of the challenges is to understand what the latency of the devices are that you're putting in. So you have to understand from any given manufacturer, how long does it take if, for example, I'm taking an SDI input and I'm turning that into a 2110 flow. What is the time of that? And then on a piece of kit, even on something that would be what I would describe as pure IP, so a software-based solution, what is the buffer time? What's the size? And Phil mentioned this earlier, what you've got to do is you've got to look at your system as a whole and try and understand where the signal is sitting in what we would class as a traditional timing model. So it's highly likely that every piece of kit that you go through, even in a minimum delay mode, is going to add a number of lines of delay into that system. Now, some kit will automatically sync everything back to effectively line 1, pixel 1 marker from the PTP. But the challenge there is that every time you're hopping through the kit, you don't necessarily want 5 frames, 6 frames, 7 frames of delay each time. So you do need to think quite carefully about what is the point at which I'm putting the signal back to the reference. So it's not that you're losing PTP time. It's that here's pixel 1, here's line 1, and that's where my picture's starting. And I think that's one of the challenges that we face, is because, of course, in an IP world, very much unlike an SDI router, we don't actually care about the timing of the signal as it's moving around. The switch has if we're using a COTS-based solution, then the switch doesn't care where the start of the video is and where the end of the video is. And if we're switching within the destination, it's then realistically only the destination that actually has any impact on the timing of that signal. So those tend to be, I think, the biggest challenges that we see. And then, of course, you need to use that information to line the audio and the video back up again. And I think it would be fair to say that some manufacturers do that better than others. And certainly initially, when the standard wasn't quite ratified, that was one of the challenges seen in the introps. Is how far out can my audio timestamps be from my video to ensure that I'm still getting back to the same place as I started.
Right. And is this information readily available, or do you have to measure it yourself and test it?
In many respects, I'd expect the manufacturer to be able to tell you. So they should be able to tell you to some level of degree of accuracy what it is that the delay is that you're expecting. But the easiest thing to do is to measure it. And when we start putting systems together, it is quite important to be able to have an understanding of, if I have an SDI input over here, out the back of a camera, what does that mean when I start looking at it on the screen? And there are various companies out there that make those measurement devices, because what's nice about IP and what makes it quite flexible is that we can then pull the timing around depending on what we're doing. One of the key things to bear in mind, though, is that if we're inserting extra processing, we need to understand that by inserting that extra processing, then potentially our timing delays to the system will change. But I say generally, it kind of, once you've got a stable PTP solution, as Daniel said, using boundary clock in switches, then tends to work quite effectively.
Yeah, and I think just to echo that, I think the most of the systems that are deployed today are low latency uncompressed. As we start seeing 211022 come forward with compression, then we're going to have variable encode and decode times. So and that will not specify a specific compression.
Yeah.
So what you will choose may vary in terms of number of lines for the encode, number of lines for the decode, which will have some effect on the AV timestamp alignment as well. So that's why I was saying at the beginning about the workflows. It's really important to understand the complete chain and how you're going to time that up.
Okay. And Gerard, can I ask you from a switch manufacturer's point of view, the data that's available in the switch, you're providing that as the switch provider. How can we be sure how accurate that data is?
Our entire reputation is built on providing data out to the cloud vendors who build their own cloud orchestration systems, and if we didn't provide that data effectively, then we would not be in pretty much every major cloud titan on the planet. So we typically tell people that a switch is a very big Linux server attached to a very big PCI pipe attached to a very big piece of silicon. It's their server, it's their switch, it's their data. We're not perfect, but our objective is to make that switch the most available and most flexible piece of kit that they can use.
Yeah.
And that enables us to address many, many different markets and applications. So, yeah, our objective is to provide as much data in as many different APIs to fit as many different models as humanly possible. That's what enables our switches to be useful to people.
Yeah. And what is the granularity of the timing information? What's the microseconds, seconds? Or?
So it's entirely dependent on the API you choose, and that's dependent on how quickly you need it and or how flexible you are in achieving that. But for example, we have a number of different APIs. We have an API that is basically a RESTful JSON version of our CLI, so that's not terribly quick, but it's very flexible and everyone understands how to use it. We have SNMP, which is massively standardized, but clearly only as quick as you choose to sample, so very available, but I don't know, every 30 seconds, 60 seconds, 2 minutes, whatever you choose. Or we have also got an open config interface, which is a vendor-neutral, customer-defined, Google, BT, those sorts of customers-defined secure streaming protocol. Uses Google buffers, if that's what you choose, standardized models, and that is, when an event occurs, we stream it.
Yeah.
So it's very, very fast. I mean, nothing in this particular world makes any sense to be nanosecond or microsecond, but it's millisecond stroke second accurate. So something happens, like if an interface goes down on our monitoring tools, you'll see that interface down in the amount of time it takes you to move your hand and look at the screen.
Yeah, I'm just thinking specifically of, data can be very bursty going in and out of the switch. So how can you measure the burstiness of the data to some accuracy?
There's some technology that allows us to measure the buffer occupancy in our switches. So that gives you a view of, that can give you a view of the burstiness. We can measure microsecond burstiness. There are things in the switch called policers or shapers that will allow you to act on that burstiness.
Yeah. And Daniel, can I ask you, it's my understanding within a PTP system, you can have many master clocks. One becomes the global master, and that's the BMC algorithm, the best master clock
algorithm, yeah.
So how can we be sure one clock is only ever going to be master? Because we rely on the clocks talking to each other to exchange protocols, don't we? So how can we be sure one clock doesn't go rogue and assume it's going to be master?
Well, the only thing that you can do is that you also monitor this master from an external reference.
Right.
Because otherwise this master can tell you that he is perfectly in sync and perfectly accurate.
Yeah.
But maybe due to a hardware or software bug, it can still tell you that he is perfectly in sync, but in fact he's not.
Right.
So you must find an external way to be sure that your master is in sync, maybe compare it to a separate reference, and just in case this happens, remove that one from the network from an external switch.
There are things that you can do to minimize the risk. There's, typically audio devices are capable of being masters. So
Right.
you can there are techniques in the network that you can enable a port to only be a master port, so it can never be slave to a rogue audio device, for example. So, you have a ton of, it's a very useful feature in audio, point-to-point connections, but there's, in a bigger system, you know exactly where your GMs are. They're here and here, or how many you've got, right? You can turn all of the other devices, all of the other ports to be master only, and then those audio devices can never become the master.
Right, okay. Because the point I'm making with this, where I'm going with this, is that in the old SDI days, when you had your SPGs, you had an AB switchover, and it was blatantly obvious which SPG was master. But now with distributed clocks and clocks all over the system, the clocks are all on the same network, so there's no physical switch, and we just have to rely on knowing which is master, so we can possibly switch it off if it.
I mean, in that vein, I mean, this is true then of a whole host of the within an IP solution, is that your system in many respects is only as good as the monitoring that you have set there. So if you need to have an understanding of what your master clock is, that requires a monitoring system, as Daniel mentioned, and that really follows down the whole way. So when we talk about timing issues, one way of understanding whether you've got timing issues or not is to have monitoring that tells you whether you're locked to PTP, what the difference is that's sitting off there, and everything else. And I would say that one key takeaway was, if you're not monitoring your IP system, you don't know whether it's working or not. And there was certainly many times in the past, I mean, Phil will hopefully attest to this as well. We built systems, we put them together, it looked like it was working, but as soon as you fired up the monitoring, it was, well, actually half the flows are coming on one leg and half of them are coming on the other, and if I was to lose a switch, an SFP, then I'd lose my entire system. And without the monitoring, it would have not been possible to see that. So I'd say that monitoring is key, both when we're talking about timing and realistically for deploying any system.
And I think it's when you build an IP system, you start with the foundation, which is the switch and the timing. And the topology that you choose, there's lots of different ways to build the PTP architecture above the fabric. You've got to choose one that's going to be robust and allow you to maintain the fabric. So as Paul was saying, having devices that are sat on either eggs of the network without any visibility and just assuming that the ports are up and traffic's flowing, you can get into some really nasty messes when you want to maintain the system, when you want to take one site down to do some maintenance. So I think the takeaways I take away from it is build the network correctly, build the PTP infrastructure correctly, make sure that how you're going to connect your PTP architecture into the switching fabric is thought through, because what you don't want is a red and blue network which are completely air gapped and they end up moving independently, because some devices will tolerate that and manage it themselves, some will not. Will get into a mess because they won't be able to know which one they're going to lock to.
Okay, nice. We touched on the idea of multiple sites earlier, so everything we've spoken about so far has really been within the constraints of one site, one studio, or one group of studios. What extra considerations do we need to think about when we have multiple sites? So say we have an office in New York and an office in London, and we have to connect the two together. How would we do that? Paul?
So I'd say the one of the first questions would be, how much money have you got? So in an ideal world, we would leave that link as uncompressed. We could decide how many cameras we wanted to send across it. As a rough rule of thumb, if we're talking 1080p, it's somewhere around 32, maximum of 40 cameras. The issue would be obviously the cost of that kind of link. So your consideration in some respects moves from how it is that we're then pushing the data across to compression. But the other thing that we need to think about is control of that link. So if I am, I can't think of a company that would have that much money, but let's say we decided to have a 500 gig link that's pushing across from New York to London, we do need to think about how we're going to put the traffic onto that link. If we're purely relying on IGMP, it could get a little bit hairier, because you can't guarantee that you're not going to fill up one link and then not another, and so on and so forth. And that then becomes a point in time when we need to potentially start thinking about some form of SDN link control. And if we tie that back to what I would class as my Luddite broadcast knowledge, realistically, that's tie line control. So I have a link, I can put this number of signals on it, and I can't put any more signals on it than that. And there's a lot of talk about SDNs, and how complicated they are, but if we drill it down to, simple talking about what we're really saying. Effectively, it's a tie line control. And of course, the challenge is that the tie line control changes. If I do 1080i versus 1080p, I get suddenly twice as many signals. But if we step that aside, the other thing is then levels of compression and types of compression, and the type of compression is realistically then determined by the latency that we can tolerate. But you end up with a factor of those two things. So the amount of available bandwidth, number of signals, and then the level of compression and latency that I'm prepared to add because of that compression.
And I guess workflows as well. So if everything's coming back to one common place, and all the presenters and all of the studios in that place, that's fine. But if you've got the presenters at the location side, you may decide that you want to make a local mix rather than burden them with a round trip that's too latent. So it does come into some considerations of how you're going to manage the audio layer, and like Paul said, even the video layer. You may choose that the layer locally is uncompressed, and then the hop is compressed, and then again you come back out into an essence-based uncompressed. You've got to think about how that's going to impact your audio. We see with customers, they do one or two ways. They either split it and they have the cameras with the talent and location, or they bring everything back. Okay. And it provides some slightly different challenges, but ultimately one of the benefits of IP, we should be allowed to accommodate both scenarios.
Okay. And Daniel, from a timing perspective, how do we link these two sites together?
It is technically possible that you can build up two synchronized islands in terms of your one common clock that you have, which is the GPS system.
Right.
So I often hear that you only need one single clock that synchronizes everything and you must derive everything from it. Yes, but it is actually the GPS system.
Okay.
So you have GPS receivers on both sides, and as long as they are in sync, then you are also okay over long distances, synchronizing both sites separately. But what do you do when on one side the GPS signal fails, on the other side is still active? So you need some sort of backup also over the wide area connection, which is also possible, which at least can maintain frequency-wise the clock that is currently in holdover. So that you at least this clock is following the same drift or the same frequency of the first one. That is still in sync.
Okay. And if one clock was to drift, say for instance in that scenario where we had a GPS lock clock in London and another one in New York, and then the one in New York failed, what would happen to the pictures in New York? Would you see any difference? If one GPS system started drifting relative to the other?
It's only a problem if you want to combine and realign streams that have been generated on one of each site.
Right.
So then you will have a problem.
So if I was in London and I took my video from New York and tried to mix
I think it's everything will move together.
Yeah.
The problem is when it clocks itself.
Right.
Yeah.
And how the devices then behave.
Well, so
some will gracefully pull themselves in, the others will just crash them all in and bang.
Right.
And that's where you're going to see the impairment.
And are there any standards to govern that, or is it just down to a vendor's?
No. The problem is that is implementation specific.
Right.
So there is no standard in reclocking how you readjust after an outage. This is the responsibility and the intellectual property of the individual manufacturers, and that's why it's not equal on all devices. That's the issue here.
So the output will be ambiguous. The result will be ambiguous. Yeah. Gerard, could I ask you from a switch point of view, how do we make this work? Do we have two big switches on either side of the Atlantic, or just one and run more cables over? What do we do?
I guess that very much depends on the capacity and the capability of the link you have between these two facilities. We are very used to these ideas. We have connection circuits between place A and place B, and those are provided by service providers, Telstra or BT or one of those guys. You have a box that terminates in your facility and looks like a layer 2 or a layer 3 interconnect. We need to, before you can make any real decisions, you need to have an understanding of what is it that they're supplying you, or what is it you asked for, because that could easily be just a dark fiber layer 3 link. It is just like a connection. It's just like an extension of your LAN. In that case, you can run PTP across it, you can run multicast across it, you can just use it as if it were an extension of your network. But most of the time that isn't going to be the case. It's going to be an MPLS link, or it's going to be a not a point-to-point dark fiber. There'll be some translations that enable multi-tenancy and security and all those other things. They may even have a firewall in there, right? So you really need to have a very clear understanding of what you're buying. You need to make sure that you've asked for 2 links and they're going to guarantee diversity of those paths. No point having 2-7 links if the first thing they do is hop onto the same switch and then trundle across the Atlantic. So
Yeah.
there's a lot of detail in there, and I think that you probably need to have a good conversation with the guys that are providing that connectivity, with your system integrator maybe, with your IT department. There's nothing, if you have like a dark fiber connectivity that just looks like an extension of your LAN,
Yeah.
you can just treat it like an extension of your LAN. You could say, I'll have 2 diverse paths, and I'll stick another leaf over there in New York. The only thing you would see is whatever 8,000 miles of latency looks like.
I think I'm right, Paul, remembering conversation, a story you were talking about, where you were using a telco and you had a layer 2 link, but at one point you had Ethernet without FEC and another link had Ethernet with FEC. They looked the same, but it didn't work. Could you tell us about that?
Yeah, so it's actually a POC that I worked on with Phil back when we were at, I think we were called Sam at the time, I can't remember. We did a remote production in 4K between the UK and Poland. And one of the things, and I'm convinced that the network vendors thought I was insane, because I'd been told this wouldn't work. And I had sort of sat there and said exactly what Gerard said. If it's an open link, if it's layer 2, it will work fine. And I sat with the network vendor and said, yes, but you've got to guarantee me that whatever I put in one end comes out the other. Because I can test this with a wire in my office, and then at the point where I'm effectively putting your network in the way, it should just look like a wire in exactly the same solution. And so I trundled off to Poland, and Phil stayed at home in the UK, and we thought we'd connect it up and everything would just spin to life, and it took us a short while to make it work, and effectively. Pinging the signal at every hop, we discovered that the last vendor, so despite the fact that they'd said, no, it's completely transparent and we've got no equipment in the way and everything else, they had some form of firewall or monitoring equipment sat over that link, which meant that it wouldn't pass FEC. So whilst we'd had FEC set up on the link so that we could guarantee that we didn't have any errors across it, the fix for this problem was to turn FEC off so that we were just pushing the traffic across. But it was one of those, it's so obvious, but I can't remember how long it took us to fix. It was quite a few hours, and it was quite frustrating. Yeah, so it's, there are some hidden challenges there, but it goes back to what Gerard said. You've got to understand what it is that you're purchasing. In that case, we had multiple vendors. I think there was 4 different link vendors within that conversation. And to be fair, the guys that I'd sat there and asked the same question to about 6 times were 100% open, and it was only that last link supplier that wasn't. So.
And I think you've got to check also that the statement on diversity. So it may well be that most of the paths are very diverse, but as we found on the last mile, they were in the same trunk. So even though it's separate paths, someone severs the trunk, that you lose both paths in the last mile. So I think there's lots of challenges, there's latency issues. I think if you're going to do that application, you're either having -7 or you're going to have some sort of forward error correction, which will ultimately affect the latency in the system. And as Gerard said, in terms of topologies, it's really up to you how you want to build it.
Sure. Okay, so my last question is, what single piece of advice would you give to any broadcaster wanting to move to 2110? So Daniel, could we start with you?
I can only say take care about the right timing infrastructure and make it right and find the right partner.
It's all about the timing and get some decent monitoring in there as well.
Yes.
Phil?
My only comment would be is you've got to treat this as a system, not as boxes. And you really got to understand what you're trying to achieve, the types of vendors you're going to have as part of that project, what the limitations are of the technology you're choosing, and really work through it from a workflow perspective to make sure when you get to start deploying the system, you're not going to run into some of the gotchas. And then there can be a number of gotchas from device immaturity, some of the workflows around multiple streams of audio, multiple levels of audio. And I think it's really good to sit down as early on as possible in that process to mitigate a lot of that as you start building up the system.
Okay, Gerard.
I'd echo Phil's point. These are complex systems, and it's very difficult for any one particular vendor or provider to understand all of the layers. And so to me, the most important thing is you go out and you engage with potential suppliers of all of the things you care about: the network, the timing, the system integrator, the vendor, the orchestrator, the monitoring, the ... If you just talk to one, if you only get one view, it'll be a skewed view.
And Paul.
Yeah, I mean, I think I sort of echo what Phil and Gerard are saying, and what Dan was saying, because I mean, you know, we need to think about this as a system. I go back to what I said before. If you don't have monitoring, you are pretty stuck. I mean, the key thing is, of course, in an SDI system, we can unplug the cable. We can either look at the end of the cable, or we can insert something where that cable was. If we unplug a cable in an IP system, it goes away. There will no longer be a flow there. And not only that, you probably killed 5 flows, 6 flows, 20 flows, depending on the size of that connector. And because of that, we need the monitoring system should be then the bit that's telling you what's there, what's potentially going wrong, and that's a different mindset. And of course, Phil mentioned this earlier. It's a full duplex connection. Sorry, it was Gerard. Full duplex connection, and so we've got signals going in both directions. And without a monitoring solution, it's very difficult to understand what's going on. And whilst there are a lot of very, very good test equipment out there that will show you your flows on the switch, that doesn't help you at your edge point. So it doesn't tell you. It tells you your flows are in the switch. You can look at your multicast that are within the switch, but it doesn't tell you whether your endpoint's working or not. And that's what the monitoring will enable you to achieve.
Nice. Thank you. Do we have any questions?
Yeah, here we go.
Hello. If you're a sort of governing body or a federation and you wanted to deploy a large IP solution, how would you, if they've got to go different facilities providers, different IP solutions, different trucks, how do you offer the assurances to them that the signals are going to be okay, that the network's going to be okay, and that the timing's going to be okay without us having to go back down to baseband as a protection?
I think if you're asking me directly, Tom, the answer to that is monitoring. So we need to be able to monitor that switch. You as a supplier, and certainly in terms of handoff to your end customers, it's if you're handing off directly in IP, you need to have an agreement of what that looks like. What is the demarcation point? What's the standards that we're using? It could be that the best way to do that is not with 2110, but with 2022-6, for example. And if we're working like that, then we can guarantee I've given you video and I've given you audio and they're timed together. And then you're not relying on your broadcaster to have the PTP generation and everything else to be able to line those individual flows back up again within their receive point. But I think monitoring is sort of a key point to that. I sound like a broken record now, but realistically, you can't unplug it and go, well, I'll just see what we're looking at.
Yeah. You wouldn't want to put them into your switch, so
No, potentially not. But there are a number of companies now that are providing either software or hardware network address translation, and the best way to think of that is a firewall. And so what you can do within your system is you can say, I'm providing you a multicast on this address with this IP, and then internally you can route anything to that point. But then looking back into the system, they're not going to be able to go back. They're also not going to be able to inject any noise. You can guarantee a physical level of security, certainly if it's a true hardware NAT.
Sorry.
So I was just going to say, I think there's the making sure the flows are the same essence and making sure timing. That what you really want is a convergence point, because you want to avoid people having the same source address IPs and multicast, which is the one that's likely to catch most people out. So you can either do that with a NATing switch, and then it's carved up so that people can converge on that. Or if there's essence type change, you will go back to video in some shape or form, or some really vast timing adjustment that needs to be done. There's multiple vendors making cards that come IPA and retime, repackage, put it back in there. It depends on the distances from the truck's infrastructure to the central point and what you want to do with it. But there's variable switches available that will do the NATing for you.
I think functionally that's spot on. You need a firewall. So it's a fire hose firewall, which is capable of NATing, so that you can agree on a interchange format. You can do the firewalling to prevent stuff you didn't want to get in. I think ISO 4 has a role here. You'd imagine truck A, facility A, truck B, facility B, they have their own ISO 4 registries, and at some point, whilst it's not standardized, those guys need to talk to each other. They need to filter the content, decide what they're going to expose. They need to have that conversation. In the IP world, there's a thing called an IPAM, IP address management system, and there's nothing to stop, and DHCP, right? I mean, these things make life quite easy. So endpoints can connect up, be given a set of addresses, they can publish those back into ISO 4, and then you can understand what is available between facility A and facility B, and you can be sure that the bad stuff doesn't go either way.
Okay, one last question.
Okay, hold on.
If I were a student and I was wanting to take additional classes that would help me in understanding or maintaining 2110, what kinds of classes outside of broadcast should I take? Networking, web architecture, JSON?
I would, so if that was right now, that's a difficult question. There is a skills gap, I think. And there's a question about whether a broadcast engineer should become an IP engineer or an IP engineer becomes a broadcast engineer. It's somewhere in the middle. I truly hope that in 2 years' time, we've got beyond that. We've got to the point where the systems are monitored, that the data available in the network has been pushed up and turned into information that is broadcast engineer information, not network engineer information, that we are logging and monitoring so that what becomes intelligent is a thing that says, well, I think your application is broken, or I think your network is broken. And maybe there's a point where those two guys have to talk to each other and they can talk a single language. I think I would say that in 10 years' time, we're going to be looking to have lots of this stuff starting to push into the cloud. So personally, if you were starting now, I'd go and learn about AWS. Probably doesn't fix it.
Or a competing.
Yes.
Sorry. Paul, have you anything to add to
Yeah, I mean, I think it's a very interesting question, and part of it is how much you really need to know and understand. And Phil touched on this earlier. What we see is manufacturers within the market, whether that's VSM, whether that's Axon, BFE, High as another example from Broadcast Solutions, and what they're doing is they're removing that complexity for you. So Phil mentioned going into the switch, looking at the flows, providing you with named flows rather than IP addresses. In a former life, I used to say if you've got to enter an IP address or a multicast address, you failed, because no one should care. All you care about is I have a signal. That signal is called input 1, camera 1. And that's realistically all you should care about. So as we move forwards, I think there'll be less and less reliance on being able to physically understand the network, because a lot of these tools will do it for you.
Right. When things are working correctly, that approach works very well. When things start to break, if you don't understand how the underlying system works, quite often troubleshooting becomes a very hit or miss.
I think this is where the monitoring aspect comes from, and everybody.
But I think we have to remember that IP hasn't just come into the broadcast space. We've had editing and MAM and playouts. I think if you've got a good understanding of a broadcast system, you generally have a good understanding of fault finding. And it's been relatively easy in the past. So like Paul said, you just get a BNC, stick it on test and measure and find it. You just now got to know the tools and how to work back through the system to really understand where that problem is, because it's no longer a unidirectional connection. You've got multiple signals traversing through multiple boxes, and it's really identifying exactly where the point is where it's broken. And you have to rely on the tools. As Gerard will testify in the cloud, they don't run around racks checking to see exactly which server or There's the tools that will say, hey, maybe it's this area, it's this rack. And I think it's really the training needs to be on the application layer rather than trying to kind of really retrain the entire industry. I think that this technology is an enabler for new ways of working, but you've got to really harness the tools that are available, and they will evolve. You see it. You see even the traditional test and measure vendors are now rolling a lot of IT functionality in to allow them to look at beyond the actual video signal itself.
I think what's coming over to me here is this is a bit like the Schrodinger's cat experiment. You know, you take the box off the lid and you destroy the experiment. That's sort of what's happening in IP. Hence the reason you can't just pull the connector out and test it, because the system is so dynamic. It's very difficult just to pull the cable out and test that. Just finally, Daniel, have you anything to add to that?
I think everything has been said. I mean, the monitoring system must reduce the complexity.
Yep.
So this is an evolving process. We're not yet on the finish line. We need the experts from both worlds still to make the system work, but those systems will evolve, and the monitoring will help that everybody can understand where the fault is.
Okay. Well, our time has come to an end, so if you haven't registered on the broadcast bridge, please do. But if you could just show your appreciation for our panel, please. Paul Harding from NEP, Gerard Phillips from Arista, Phil Myers from Lawo, and Daniel Boldt from Meinberg. Thank you. Thank you.
Thank you, everybody.